Hello, in this video I'm going to take you through questions 6 to 12 of the 2018 Higher Chemistry paper. So question 6a, you've got this molecule here and straight away you can see it as an ester molecule because it's got an ester link in it. So then you're asked to name the type of reaction that occurs when retinol palmitate is broken down. So if you are breaking down an ester, it will be a condensation reaction. So that would then break down to form retinol and the other product. So then it says to write the molecular formula for retinol. So because retinol ends in well, that suggests it's an alcohol. I need to just try and find my tape tool now. So if we were to split the ester link, it would break here, and the alcohol side is the side with the single bonded oxygen, so that would be this side. So the molecular formula for retinol would be C20H29OH. So don't forget to add the H back onto the hydroxyl, the hydrogen ion. And you don't need to draw it fully because it's just asking for the molecular formula, so don't waste your time drawing a row of 20 carbons and all of those hydrogens. So then B part 1, describe how free radicals are formed. So they're formed when UV light enters the cell and it causes the covalent bonds and molecules to break. Okay, so the main bit here is that they're exposed to UV light. So then we've got a free radical chain step, and you're asked to state the name that's given to this step in the chain reaction. So we have free radicals on both sides here. So remember, the free radical you can spot by the dot symbol here. There's a free radical on the reactant side, a free radical on the product side, which means it would be propagation. The other two steps are initiation and termination. So in initiation, you won't have a free radical reactant, but you'll have a free radical in products. And in termination, it's the opposite around. You won't have a free radical product because the free radicals are all stabilized. Okay, and then part 3, state how free radical scavengers prevent further chain reactions. So they prevent further chain reactions by stabilizing free radical, or you can say that they donate unpaired electron to the free radical so it becomes stable, but it's generally about it stabilizing the free radical because it's got an unpaired electron. Then circle a peptide link in the structure here. So the peptide link can also be called an amide link, and that's the one with the Chon elements in it. So that would be one here. You could have also circled this one, or this one, or this one, or this one. And then we've got question C part 2. It's formed palmitoyl pentapeptide 4 is formed from palmitic acid and 3 different amino acids. Draw a structural formula for the amino acid serine. So we need to work out what all the amino acids are. So I'm going to break all of the amide peptide links. Okay, so this is 1 amino acid, 2, 3, 4, 5, 6. Now there's 2 of the threonines and 2 of the lysines. So that means if we look to see, so that there's 2 of them and there's 2 of them. So we're looking for serine. The other option where there's only 1 of them is the palmitic acid. Now, if we look at the structures here, this molecule here is going to end up as being only a carboxylic acid because it doesn't have an amine group at the other side to make it an amino acid. So that must be the palmitic acid, which means our serine amino acid is this one here at the end. So if we draw that out fully, we've got N, and don't forget that N becomes an NH2, C, CH2, OH, H, and then the carboxyl group at the end. Okay, just make sure you show correct connectivity of your atoms, so just make sure the hydroxyl group, the oxygen's bonded to the carbon there. So move on to question 7. Draw a circle around an isoprene unit. So the easiest way to find an isoprene unit is to find a branch. So something that looks like it could be a branch. So I'll pick this one here. So that's going to be our branch that's usually on carbon 2. So that means this is carbon 2, 1, 3, and 4. So you step one back and then find a chain of 4. So that would be one isoprene unit. Okay. You could also have this one here. So humulene has a molecular formula C15H24, meaning the class of terpene to which it belongs. So the class of terpene is dependent on how many isoprene units make it up, which you can see from this table here. So if it's got 15 carbons, each isoprene unit contains 5. So 15 divided by 5 is 3, which means it would contain 3 isoprene units. So the class of terpene is this one here, which I don't even think I want to try and say, sesquiterpene. Then B part 1, we've got a numeracy question here. So 1 dose of a flu vaccine contains 10.96 milligrams. And we need to calculate the mass of squalene required, for this mass here, to produce 500,000 doses of vaccine. So that means we need to times this by 10.96 by 500,000. If 1 dose needed that much, 500,000 doses will need 500,000 times as more. So that comes out as 548 4 zeros. So that's in milligrams. We want it in kilograms. So you might find it easier to change it to grams first. So there are 1,000 milligrams in a gram, so we want to divide this by 1,000 to put it to grams, which gives you 5,480 grams, which then to get into kilograms, you divide by 1,000 again, which is 5.48 kilograms. Yeah, there are some conversion factors at the back of the data booklet if you're really not sure. It's got milli being 10 to minus 3, that's in respect to like grams. And 10 to minus 3 is just 1,000 or 1,000. So then part 2, state the number of moles of hydrogen needed to fully saturate 1 mole of squalene. So when you're reacting with hydrogen, you're doing an addition reaction. You're doing an addition reaction and you are breaking the double bond and adding hydrogen across it. That means that you will need 1 mole of hydrogen for every double bond in the molecule. So there are 1, 2, 3, 4, 5, 6 double bonds. So you will need 6 moles of hydrogen to fully saturate that molecule. Here, name the type of reaction taking place. So if you look at what you're actually changing here in this molecule, so things that we've added on, so there was a CH2 here before, now it's a CH3, so that means we're adding on a hydrogen there. And then the other thing that's getting added on is this OH. So altogether, we've added water to a molecule, which means it would be hydration. Then when terpinol is heated with copper 2 oxide, no reaction takes place. Explain why. So copper 2 oxide, remember, is an oxidizing agent. So if it reacts with copper 2 oxide, it means it can be oxidized. However, that molecule is a tertiary alcohol, so it cannot be oxidized. That's why no reaction takes place. So it's because it's a tertiary alcohol, so it cannot be oxidized. Question 8, bond enthalpies. So we've got bond making. Should be on the other side. It's too early. Bond breaking. And then bond making. So this one's quite good because it shows you the pictures, so you can see what bonds making and breaking. So you are breaking 1, 2, 3, 4, 5, 6 carbon to hydrogen bonds, and then 1 carbon to carbon bond. You are making 1, 2 carbon to hydrogen bonds, 1 carbon to carbon triple bond, and then the 2 hydrogen to hydrogen bonds. Okay, so then if you look up the bond enthalpies on page 10 of the data booklet, so carbon to hydrogen is 412, so that's 6 times 412. Then carbon to carbon, single bond is 348. I'll add that up after, so then that would be 2 times 412, and then this would be carbon-carbon triple bond is 838. And then hydrogen is 436, that would be 2 times 436. Okay, so I'll add these up. Okay, so when you add those up, that's what you get. So remember, bond breaking is endothermic, so you have to put energy in, so it's a plus. And bond making is exothermic, so you get energy out, which means it's a negative. Now you just need to take the net energy change for these two, so you add them together. So that'd be 2820 plus minus 2534, which gives you 2820 minus 2534 plus 286. And that'd be kilojoules per mole. So overall, this is an endothermic reaction because energy goes into the substances. So we Hess's law question. Got our target equation, and then we're given the other equations. So if I number these 1, 2, and 3. So the first thing in our target equation is this 3C, which the carbon is here as a solid. So we need 3 moles of that. So that means we need to times reaction 1 by 3. We don't need to reverse it because the carbon's on the correct side. Then we want H2. So H2 is in the second one, and we need 2 moles of it. And again, it's on the right side, so that I'm timing that one by 2. And then lastly, we've got the C3H4, which is here. That's got the right number of moles. However, it needs to be on the other side of the reaction, so we need to reverse number 3. So if we change those energies, so 3 times 394 for reaction 1, it means it comes out as minus 1182, still negative. And then 2 times negative 286 is minus 572. And then if we reverse the last one, that just becomes plus 1989. So now all we need to do is add all those together. So minus 1182 minus 572 plus 1989 gives you plus 185 kilojoules per mole. Okay. Your calculator obviously won't show you the plus sign, but if for enthalpy changes, if it comes out as a positive number, then try and remember to put the positive symbol in front of the number. So 8C, enthalpy of combustion of propine is that. So that means 1 mole of propine gives you minus 1939 kilojoules. Okay, and then you're to calculate the energy released when 1 kilograms of it is burned completely. So we need to convert the moles to a mass. So the mole, 1 mole is 40 grams. So we know 40 grams gives us that. So we're trying to find out how much we would get if we had 1,000 grams, which is what a kilogram is. So we find what 1 gram is first. So that divided by 40. And then we times it up to 1,000. You put all that into your calculator. 1939 divided by 40 times 1,000 is 48475 kilojoules. Okay. Lots of energy. And it'd be negative. Sorry. 6 thermic, always for combustion. Okay, so then part 2, calculate the mass of air in grams required to burn 1 gram of propane. So you're just using this relationship here that you're given in this equation. So we are trying to work out the mass of air. So that is 4.3 times the mass of oxygen for complete combustion. So we need to work out how much oxygen we need first. So we need to work out how many moles of propane we've got. So propane's mass is 40 grams. So if we've only got 1 gram, the number of moles would be 1 divided by 40. So that would be 0.025. Because it's a 1:4 ratio, that means we would need, so if we've got 0.025 moles of the fuel, we need 4 times the amount of oxygen. So that would be 0.1. So then if we change that to a mass of oxygen, so the number of moles is 0.1 of oxygen, and the gram formula mass of oxygen is 16 times 2, because each oxygen is 60, so that's 32. So that means you would need 3.2 grams. Okay, so then we've got 4.3 times 3.2, which is 13.76 grams. Okay, so you need to use the balanced equation for this. Then 8C, part B, table shows the mass of air required for 1 gram of different fuels. Suggests why methanol and ethanol compared to other fuels require less air to burn 1 gram. So if you look at the difference between the fuels, you've got ethane and propane, so they're alkanes, and then you've got methanol and ethanol, which are alcohols. So the difference between them is that the alcohols that need less air already have oxygen in them, whereas the alkanes don't. So they require less air because the molecules already contain oxygen. 9A, using flowchart suggests 2 ways to maximize profit in this industrial process. So maximizing profit, you're usually looking at recycling things. So you could recycle, what can you recycle here? So you could, so they're already recycling the waste gases, so that's going to be maximizing profit already. They're recycling waste gases. They could sell the liquid byproducts. So anything that's a byproduct means you're not wanting to keep it for your particular reaction, but there could be someone else somewhere in the world that wants it. So you could sell your byproducts. Other things you could do would be to use a catalyst, so that you wouldn't need to run at such a high temperature, and also the feedstocks that they use in this reaction are pretty cheap. So they're not very expensive, which would help to maximise profit as well. Main process used in separator 2 to separate ethane 1,2-diol from larger liquid byproducts. So because you're separating liquids, that would be distillation. Okay, so anytime you're separating liquids, it's a distillation process. And explain fully why ethane 1,2-diol is more viscous than propan 1-ol. So viscosity is its ability to flow. If something's very viscous, it doesn't flow very easily, and that all comes down to the van der Waals forces between the molecules. So ethane 1,2-diol has 2 hydroxyl groups, whereas propan 1 only has 1 hydroxyl group, which means the hydrogen bonding in ethane 1,2-diol will be much stronger than the hydrogen bonding in propan 1-ol, which causes the ethane 1,2-diol to have a higher viscosity. Draw structural formula for a diol that contains 3 carbon atoms. So here you're just really wanting to draw a propane chain with, and then add 2 hydroxyl groups onto it. So you could put them on either end carbon, you could put them on the first one and the second one, and things like that. Then 9D part 1. Ethane 1,2-diol has been found to be harmful to animals. So we've got another numeracy question here. Oh no, preparing a standard solution. Numeracy 1 comes after. So describe the procedure to prepare this solution. So you're measuring out a liquid, which means you would measure out the 20 centimetres cubed of ethanol with the pipette and add it to a volumetric flask. Then you would fill the volumetric flask up to the graduated mark on the neck of the flask with distilled water until the bottom of the meniscus is on the mark, and then you would stop it and invert it. So because that's a liquid you're using to make up the solution, you would need to use a pipette to measure it out. Then part 2 is the numeracy 1. So, an affected animal must be treated with 9 doses. So, that's important, you need 9 doses. Each dose contains 5 centimetres cubed of ethanol solution for every kilogram body mass. So we're trying to work out the total volume of the solution needed to treat a 3.5 kilogram animal. So per kilogram, they need 5 centimetres cubed. So if it's 3.5 kilograms that the animal weighs, then we need to times that by 3.5. So 5 times 3.5, that's 17.5. Okay, that's just for 1 dose. So, but they'll need 9 doses altogether. So then the total volume would be 17.5 times 9. 157.5 centimeters cubed. Okay. Then part 3, ethane 1,2-diol is harmful because it disoxidizes in the body to form glycolic acid. Draw a structural formula for another possible product for the oxidation of ethane 1,2-diol. So a primary alcohol, which is what ethane 1,2-diol is, because the hydroxyl groups are at the end, could also form a ketone. So you, not a ketone, sorry, an aldehyde. So you could draw this instead. So instead of having the carboxyl group at the end, here you'd have the carbonyl group instead. And then glycolic acid can be neutralized by sodium hydroxide to form sodium glycolate to give a formula for sodium glycolate. So when you neutralize a organic acid, what happens is the hydrogen ion comes off the carboxyl and the sodium goes in its place as an ionic bond. So you can draw the charges of the ions that form if you wish, or you would still get the credit if you drew it like this. Okay, but just as long as you take off the hydrogen ion on the carboxyl group and add the sodium ion in its place. Lovely question, this one. Molar volume. So what you would want to do is set up talk about setting up an experiment here that would generate a gas. So if you so you've got carbonates, metal carbonates there, which means if you react them with an acid, because they're bases, they would neutralize and form carbon dioxide. So you could generate a certain amount of carbon dioxide gas and measure the mass of it, a given volume, to work out the molar volume. However, you do have cylinders of gases, so you could just use a defined volume of them. You've got 500 centimeter cube flask here, so you could fill the 500 centimeter cube flask with 3 different gases here out of the cylinder and measure the mass. And then what you would want to do to work out the molar volume would be to use this relationship. So number of moles is equal to the mass over the molar volume. So you're trying to find out molar volume, so you'd rearrange this to work out what the molar volume is. Other things you want to mention would be like creating a vacuum and also keeping the temperature and pressure the same, because molar volume can be affected by temperature and pressure. Yeah, just want to talk about an experiment like that. Talking about reacting so if you reacted a metal with the hydrochloric acid, you create hydrogen gas. So discussing how you create the gases through the reactions as well helps a little bit, you to show a better knowledge of chemistry. So then 11A, describe a procedure to accurately weigh out a 50-gram sample of iodized table salt. So you want to to accurately weigh out anything, you would weigh the weighing boat and the contents. So this is you describing weighing by difference. So you have your weighing boat and add the amount, 50 grams that you need to the weighing boat. Then you would decant the table salt into whatever or flask you're putting it into, and then reweigh the weighing boat at the end, and the accurate mass that you've transferred is the difference between those 2 measurements you've taken. The other thing you can do is just use the chair function. So put the weighing bolt on the balance, tear the balance, and weigh out 50 grams of salt. You can do it that way as well. So we write the ion electron equation for the oxidation reaction. So oxidation is loss of electrons. So if I look at the iodide ion first, that's going from negative to neutral, so that's losing electrons. So that means you would just look up in the data booklet the oxidation of iodide reaction, just copy it out as you see it. However, remember in the electrochemical series, it's reduction reactions that are shown, so you'd have to copy it from right to left. C part 1. Calculate the average volume in centimetres cubed of sodium thiosulfate solution that we used to determine the moles of iodine released. So remember, when you're calculating the average volume of a titer, you don't take into account the first one because that's a rough titration, and then after that it's only results that are concordant, so that's within plus or minus 0.2 centimetres cubed of each other. So these two are concordant, so that means the average would be those two added together divided by 2, which would be 9.5 centimetres cubed. Okay, and then calculate the number of moles of iodine released from 50 centimetres cubed of the standard salt solution. So we're titrating with sodium thiosulfate, which is this one here. So that's if I write that on the side, Na2S2O3, and then we've got the iodine we're trying to calculate the moles of. Okay, so it's a 1:2 ratio. So the sodium thiosulfate is a solution, so that means we're going to have to use N, B, and C. So the concentration goes up here, so that's 0.001. You don't really need the last zero. Anyway, the volume is what we just calculated in the last question, but you need to turn that into litres, so you need to divide it by 1,000. So 9.5 divided by 1,000 is 0.0095 litres. So we can now work out the number of moles of sodium thiosulfate, so N equals B times C. So that comes out as 9.5 times 10 to the minus 6. Because it's a 1:2 ratio, that means you're going to have half the amount of iodine, so that would be 4.75 times 10 to the minus 6 moles. However, just need to double check because it's talking about 50 centimetres cubed of the standard solution. Please check what the sample volume is. So sample volume is 50 centimetres cubed, so that's fine. So here. Sometimes you'll need to scale up. Okay, so A part 1 suggests 2 ways in which structural features increase germ killing power of phenol compounds. So you're wanting to look for patterns here. So find the ones that are best germ killing. And see what the difference is. So if the best one's the one with the most chlorine on it, so you could conclude that if you add chlorine atoms, it becomes better killing germs. Or even if you add, so if we compare this one, and this one, which are all the same except for the branches, if you add more branched groups or alkyl groups, that will increase the germ killing ability. Also this one here, that's C3H7, that's even better at germ killing. Okay, so either of those things, so longer branches or adding more proteins. So then, following these rules, name this molecule. So it tells you the first rule is that the hydroxyl group was on carbon 1. So this means that this carbon here is going to be carbon 1. And then it can be numbered clockwise or anti-clockwise, but the numbers should be assigned so it's the lowest possible. So that means that we probably want to go in this direction. So this is carbon 2, 3, 4, 5. Because if we go the other way, we end up with a branch being on carbon 1, 2, 3, 4, 5, 6, which gives you higher numbers. Okay, so 2 or more identical atoms are present. Use one of the prefixes di, tri, or tetra. The names of the atoms or groups attached to the ring are listed alphabetically. So if we scroll back up to see the names of these ones, you can get some inspiration from these. So if they've got a methyl group on them, which are the one we're trying to name has, so it's got methyl groups and a chlorine group. So if you look for one with chlorine, that's got chloro, so that would be the name of the chlorine branch. And then the one with the methyl group is just methyl. Okay, so chloro comes before methyl in the alphabet. So that means it would be 2 chloro, because the chlorine's on carbon 2. And then our methyl branches, because there's 2 of them, it's dimethyl, and they're on 4 and 5, so it'll be 2 chloro, 4, 5, dimethyl phenol. Okay. So, percentage yield question. Calculate the mass of phenol in kilograms produced from 117 kilograms of benzene. The percentage yield is 90 grams. So, we work out the theoretical yield first. We'll always have to do that in a percentage yield question, so you can always start there if you forget what else to do. So we've got 1 mole of benzene should give you 1 mole of phenol. I'm not going to do it by the direct proportion way. I'm going to do it by using the mole relationship. So if we have 117 kilograms of benzene, we need to work out how many moles that is. So N is M over GFM. So we have that many grams. The gram formula mass of benzene is 78. So put that into your calculator. 700, 78. So that means that we've got 1,500 moles, which means we could make 1,500 moles of phenol because it's a 1-to-1 ratio. So that means that the mass we could make would be N times GFM. So that would be 1,500 times 94, which is 141,000 grams. So if we put that into kilograms, that would be 141 kilograms. So the percentage yield is only 90%, so we want to find 90% of our theoretical yield, which is 141 kilograms. So if you find 90% of that, that means you get 126.9 kilograms of phenol. Yeah, and we're finished. So last question, naming the product formed, the other missing product formed in this process. So easiest way is to score out anything that appears as a product and a reactant. So we'll score out that benzene ring. Then we've got OH, so we'll score out that OH. Okay, so we're left with CH3, CH3, and then a single bonded oxygen. We are adding a hydrogen ion, so it's most likely the hydrogen is going to go here, which means this oxygen will then form a double bond to that carbon. It's not the nicest looking carbonyl group that's ever been drawn. Okay, which means that you end up making propanone or propanone. Okay, and that's that.